Hello everyone, I'm Sharmin Sara and today I'm going to show you how to convert a C code to MIPS. So the problem that we are going to solve today is of finding Narayana number. So let me first tell you what Narayana numbers are. Narayana numbers are numbers that form a triangular array of natural numbers which are called Narayana triangle. So here's the formula for finding Narayana number, which is 1 by n into n choose k into n choose k minus 1. So if the value of n is 8 and the value of k is 3, then the Narayana number will be 196. Similarly, n is equal to 1 and k is equal to 1, so the Narayana number will be 1. So let's just have a look at the C code now. To convert this C code to MIPS, we will need to open the Mars simulator that I'm using right now, and we will now open a new file, which is file new, and then save it, Control S, and we will name it whatever we want, and I'll be naming it Narayana. So the first thing that we do in the C code in the main function is storing the values of n and k. We will do the same in the MIPS code. So I'm going to do add I s0 0 6. This line means I'm adding 6 to the register 0, which has the value 0 stored in it, and then I'll be storing that value in S0 register, which means I'm storing 6 in S0. So S0 is representing n right now. In the same way, I will store the value of k in S1, and the value of k will be 3. K is equal to 3. So I have stored the values of n and k in S0 and S1 register. So I will now copy these values to A0 and A1 registers, because I'll be using these registers for sending parameters. We could have saved these values in A0 and A1 directly, but by doing that we would have lost the values of n and k. So that's why we have use these S0 and S1 register for saving these values, and then we will copy these values to A0 and A1 and send them as parameters. So I'm going to copy them. 0. So I've copied them. I have added the value of S0 to the register 0 and then stored it to A0, which means I have stored the value of n in A0 register and the value of k in A1 register. So my parameters are ready, and in the main function I have called the function NCR. I'll do the same here, and for function calling in MIPS we use the instruction JAL. JAL means jump and link. So jump to the function that I want to call and then link the immediate next instruction's address. So I'll jump to NCR, and it will automatically save the address of the immediate next instruction. So I'll write the next instruction later. We will now go to the function NCR. Here it is. So in the NCR function, we can see in the C code that what we are going to need is I and res. I and res are temporary variables which we will need for finding the NCR, n choose k, n choose c, or n choose k, whatever we say. So first of all, I'll store the value of I add I t0 0 and then 1, I is equal to 1. So this line means that I'm storing 1 in the register T0. The fact why I'm using temporary register T0 is that the reason why I'm using temporary register is that we won't need this value of I later after the function, so we can use temporary registers. So similarly, I'll store the value of res in T1. So I have stored the values of I and res like the C code. And now one extra thing that I'll do is add T2 RA 0. Well, this line means that I'm storing the value, the address that is in the array register, which actually returns the address of the instruction which is right after the uh, JAL, right after the JAL function, because when we call this, when we use this instruction JAL, it jumps to the function and links to the immediate next instruction's address. So the address is stored in that RA register. So I'm storing it in this temporary register T2. So here we can see that in the C code we are checking whether I is less than or equal k. So we'll have the condition here. So I is less than or equal k. So here our I is t0 and k is s1. So what we will do is BLE, which means branch less than equal T0 A1 loop. Well, this line means that if the value stored in the register T0 is less than the value stored in the register A1, it will jump to the label loop. Otherwise, jump exit. So, as you can see in this function of C code, that if I is less than or equal k, it will go inside the loop, otherwise it won't. So if B is less than equal BLE, so branch is less than equal T0 A1, so it will go to the loop. So I will now write the function loop. Here is loop label. So what we do in the loop is multiply n to res, and then we decrease the value of n by 1. So the first thing that we are going to do is multiply mul t1 t1 0. So this line means I'm multiplying the values stored in T1 and A0 and then storing it to T1. So which actually means that I'm multiplying the values of n and res, which means 1, and then storing it to T1, which means res again. And then what I'm doing is add I A0 A0 minus 1, which means I'm decreasing the value of n by 1, like line number 16 in the C code. And then I am increasing the value of T0. So add I So add I T0 T01, which means I'm increasing the value of I by 1. So I'm done with this loop, and then I'll jump back to the condition, because in this loop we can see that we increase the value of I and then check whether the condition is true or not. So we are done with this part. So I will now write the exit that I have written here in the condition. So the exit part would be add A0 0 to A1, which means n is equal to k. So this line means I'm using the value of k as a parameter for calling the function fact, which is jar fact. This fact is the function for finding the factorial for of a number. So similarly, this jar instruction will jump to the function fact and then link to the immediate next address. So jar fact means it will jump to the function fact and link to the address of the next instructions. So before writing the instructions of fact function, I'll write the next instructions here, which are divide, which is div p0 t1 and p0. This line means I'll divide T1 by V0 and store it in V0. So T0 was the res that I calculated in the loop, and as we can see in line 19, that res is divided by fact. So the function fact will return the value in the register V0, and then we will divide T1 by V0 and then store it in V0. So that will be the result, and then we will add RA0 T2. So which means we will store the value of T2 in array. See, in the NCR function we had stored the value of RA in T2, and then again we are storing the value of T2 in RA. So and then it will jump to RA. So that's what we have to do after returning from the function. So we will now write the fact function. So here it is. In the fact function, what we do is calculate the factorial of a number. Here we can see in the C code. So it is a recursive function, as we know that a recursive function has two parts, which are base case and a recursive call. So even in MIPS we will have two parts, which are two labels, which are base and recursive call. So before doing that, one thing we are going to do is we will be using stack pointer register for storing the values of RA register and A0 register, because this is a recursive function and it will be calling itself again and again. So after we use JAL instruction, it will jump to the function and link to the immediate next address. So it will be writing to RA register again and again, and the previous values will be lost. So in order to have all the values stored, we will be using stack pointer where all the values will be getting stored in a stack, and we will just push and pop those values and use them according to our need. So what I'll do now is addi sp means stack pointer, sp minus 8. Here I have taken the stack pointer to 8 steps down, which means if the stack pointer was pointing at the address 420, it will now point to the address 412. So I will now store word as RA0 So this line means I am storing the value of RA to the stack pointer having the offset 0. Offset 0 means I'll be adding 0 to the value of stack pointer address. So which means stack pointer will be in 412, and I'll store the address that is stored in RA to stack pointer. Similarly, I'll store A0 so here I have written the offset 4. The reason behind doing that is that we know that there are 4 bytes of difference in the memory addresses, so we can't write 0 here. So we are done with the pointer thing. We will now write the base case, which is here we can see the base case is this line number 4 and 5. If n less than or equal 1, then it will return to 1. So we will write the same thing here. So BGT, which means branch greater than A0 1 recursive. This line means if A0 is greater than 1, then it will jump to the recursive function, and if it doesn't, then what will it do? We'll now write it here. So if the base case is reached, what we will do is addi v0 0 1. So if a is not greater than 1, then we will return 1. So we will store 1 in v0. As we know that v0 register returns the values of functions, so this line means that v0 will have 1 in it, and then what we have to do is load word RA0 SP. So we are doing just the opposite of these lines 29 to 31, where we had stored the values of RA to a stack pointer. We are now bringing the values from stack to RA and then A0. So we have popped the values of RA and A0 from the stack and stored them in the registers. So we have done exactly opposite of what we have done in lines 31 and 32, where we had stored the values from RA and A0 to the stack. Here we are bringing those values from the stack. So after doing that, we'll have to bring the stack pointer where it was before. So we will bring it back to its place, sp. So we will bring it back to its place. So initially we had subtracted 8 and the stack pointer went to 412 address from 420. So we will now take it back to 420 by adding 8. So we have taken the stack pointer to its previous place. So after that we will so once the stack pointer is back to its place, we will jump back. Sorry, gr. So when the base case is done, it will jump back to ra. So we're done with this, and I'll now write the recursive function. So when n is not less than or equal 1, it will go to this line, which is line 7, n into fact n minus 1, which means n will be multiplied to uh, n minus 1 fact. So what we are going to do here is, first of all, addi a0 minus 1. Why I have subtracted 1 from a0 is that here we can see that in this line fact function is being called again, but with the parameter n minus 1. So the value of n has been decreased by 1. So that's why I have changed the value of the parameter. So now I'll call the function jal again. So it will jump back to the function fact and then link to the address of immediate next instruction, which are going to be same as we have done in the base function. So load word ra0 sp, then load word a0 4 sp. So we're doing the same thing here, because either way we have to change the we have to take the stack pointer to its previous place and get those values of ra and a0 from the stack. So we will now have to take the stack pointer to its previous place. So here it has done that, and now we will have to do the last thing, which is multiply v0 a0 and then v0. So this line means I am multiplying v0 to a0 and then storing it back to v0, like we have done this here in the C code, where we are returning the value of n into fact n minus 1, which means we are if our n is 6, then we will be multiplying 6 to 5, then 4 3 2 1, like that. So after all these are done, we'll be multiplying them. So the work of calculating factorial is done. So we will jump back to our a that was stored. So we will now exit. So we are now done with almost all the functions, but there's one thing left, which is these lines. We have called the function MCR, but we haven't written what we have to do after that. So I'll now be writing that. As our code has reached this line, means that we have called the NCR function, we have checked the conditions, we have gone through the loop, we have exited that, then we have called the fact function, we have gone through the base case and recursive call, and then we have come here, which means most of our task is done. So we'll be doing the last things, which are mul s2 b0 s2. So then we will divide s2 s0 and then jump exit 1. So these two lines, mul and divide, are the lines mm, from so these two lines are from here, where result is equal to mck into mck1, which means we are multiplying v0 to s2 and then storing it to s2 again, and then dividing it by s0, which means n. So this, if you look at the formula again, you can see that we have calculated this n choose k and then n choose k minus 1 in till this place, which is till this line 6. Multiplying v0 and s2, we have calculated this n choose k and n choose k minus 1, and the only thing that we are left to do is division by n. So we are now doing this divide s2 by s0 and then storing it in s2. So our result will be in the register s2. So we are done with our code, so we will now run it. So run assemble. Okay, so we will now run this assemble. So if we run this, we will see that our result has been stored in s2. If we take a look at the picture, we can see that what our result is going to be. So we had taken 6 for n and 3 for k, and the result should be 50. So let's just see if our result is 50 or not. So let's just run it, and we can see that the result is now 50 in s2. So which means our code is right. So this is how we can convert a C code to MIPS code. We could also have used this button for running one step at a time and checking what happens in each step. So I'll show you that also. So here it is 0, so I'll run it for once. So as we can see that s0 has 6, which means we had stored the value of n in s0, which is 6. Then in the second line, s1 is 3, which means we have stored the value of k, which is 3, in s1. Then it goes to a0 6. We have copied the value of n to a0, and then a1 is 3, so we have copied the value of k to a1. So the ra is now this thing. This has happened because we have called the function jal ncr. So it has gone to the function and stored the address of the next instruction. So after that, we can see that t0 is 1. We had So we had initialized I with 1, so that's what has been stored here. Then t1 is equal to 1, res is equal to 1 has been done here. Then t2 equals this address, because we have used BLE on branch less than or equal. So this line has these another subline inside it. This instruction is completed by using another instruction, so that's why it has happened here. And then 80 is equal to, this is because of that BLE. And now A0 is equal to 5. Our A0 was 6 before, and now it has become 5 because we have subtracted 1. And similarly, by going through all these steps, we will find that S2 is equal to 1. Sorry, S2 is equal to 50. So we can do all these steps and see what's happening and find the result. So here it is, S2 is equal to 50. So we have converted the C code of finding now and a number to MIPS. So I hope that it will help you all. So thanks for watching.